This video is a continuation of the data notebook, and we'll be discussing use of built-in datasets and tools for visualizing data. We've already seen several examples using the built-in datasets in R, but since our usage was sort of as needed, I wanted to revisit this here to give you an easy way to find examples to refer back to. So we're going to start again with the data function. When we run the data function, it displays the help page listing all the datasets currently available on your system with a short description of each. Now note that this does not include datasets from unloaded packages, meaning that likely you have other datasets installed, but if the packages containing those datasets are not currently loaded, then the data function will not list them. So at the moment, we have not loaded any additional packages, and so the listing here really just includes all the built-in datasets. So if I run this again, but first load the ggplot2 package, you'll see that the listing of datasets changes and now includes those sets from ggplot2 as well as all those in the original listing. Now, if I were to go through this list and say select a dataset, maybe we're interested in the growth of orange trees and wanted to know more about this particular dataset. We could use the help function to get details on this dataset by typing help and then passing the name of this dataset as the argument, so orange in this case. And like most help pages, it's going to give details on the format of the data, where the data came from, as well as some examples on how to use it. So if we look at the description and format sections, we can see that this orange dataset contains a data frame with 35 rows and 3 columns, where the samples, or the rows, are the age and circumference measurements taken from a set of trees starting around December 31st of 1968. And if we wanted to use this dataset, we need to load it. And we can do that again using the data function. But this time, instead of calling the data function without arguments, we're going to pass the name of the dataset orange. Now, as an aside, if you were to look at the help page for the data function, you would see that the first argument is actually listed as an ellipse or 3 dots. And this is because we can specify multiple datasets to be loaded here without making multiple calls to the data function. To do this, you would simply add additional dataset names separating each by a comma. So if in addition to the orange dataset, we wanted to load the empty cars dataset, we would add a comma and then just write empty cars. But for the moment, we're only interested in the orange dataset. And so we're going to use the data function to load this. And to verify that we've actually loaded the data, we're going to print it out. Now notice that I used orange as a string when I pass it as an argument to the data function. But when I call the print function, I omit the quotes. And the reason for this is the data function will load the orange dataset by name and create a new symbol, orange, pointing to the data frame that contains all of the orange tree data. So if I run this block, we see that this is true. The variable name, orange, does in fact point to a data frame containing all of the orange tree data. Notice that I didn't explicitly create the name orange. The data function actually did this for us, and the name of the dataset is actually set by the creator of the dataset. So typically a variable name will match the name of the dataset, but it's always best to check the documentation to make sure this is the case. As a side note, in a few previous examples, we may have seen us load or use a dataset without first calling the data function with that dataset as an argument. The ability to do this is really a convenience in R, and it's not recommended for all datasets. In fact, it's safer and cleaner to use the data function to load all of your data, since it clearly declares where the symbol name, orange in this example, is coming from. Also, the data function has several additional arguments that allow some control over how the datasets are actually loaded. So I encourage you to explicitly use the data function when loading built-in datasets, as well as checking out the documentation to see the additional options that are available to you. Now, if you recall, when we used the data function without any arguments, we received a list of all the datasets from the current set of loaded packages. Now, if you have several packages loaded, then this list can be quite long, and finding what you want may take a little time. So if you're only interested in finding datasets from a particular package, or maybe you don't exactly remember the name of a dataset, but you know the package from which it comes, then you can specify the package name to the data function and get a listing of the available datasets only for that package. So if we're interested in seeing only the datasets from ggplot2, we could call the data function and pass ggplot2 as the package argument. And you'll see here at the bottom that the help page opened up, giving a listing of the datasets only from the ggplot2 package. Now, another use for the package argument is to specify from which package a dataset should be loaded. So let's take diamonds, for instance, which is the first data set listed here in the ggplot2 package. If another loaded package also had a data set with the same name, we could use the package argument to specify that we wanted to load the diamonds dataset from ggplot2 and not this other package. And so we see that the package argument can actually be used for both listing out datasets from specific packages or for loading those datasets from specific packages. Now, again, I'm going to encourage you to view the documentation on the data function since there are several other options that may be useful to you. And I'm also going to encourage you to use these built-in datasets to experiment with all the tools that we've discussed and even as practice runs for other analyses that you may perform. Now, we've seen how to view and load the built-in datasets, as well as how one can start to construct our own loaders for reasonably organized data. And in the notebook on data frames, we even discussed some generic functions that can help you to understand your data. So for those functions like summary and structure, I'm simply going to refer you back to that notebook and corresponding video. However, for the rest of this notebook and video, we're going to demonstrate a few plotting tools that get you started with visualizing your own data. So as usual, we need to start with the dataset. And so this time we're going to load the faithful dataset, which contains the duration of 272 eruptions of the Old Faithful geyser in Yellowstone National Park, along with the wait time between each of those eruptions. And instead of printing the entire data set, we're just going to use the head function here and output the first 10 lines from the data frame. And so we see that the first column contains doubles that are the duration of the eruptions, and the second column is the waiting time between those eruptions. And if you were to look at the documentation, you would see that it tells us that each of these values are actually given in minutes. Now, of course, we can use the summary and structure functions to help us understand this data, but often it's better to actually visualize or display the data in some way. And R makes lots and lots of options available to us. So we're going to start with probably the simplest one, and that's the plot function. If we wanted just a scatter plot of the duration of each of the eruptions, we can call plot and pass the eruptions column as an argument. Notice that I'm using the double square bracket notation here, since this will return our data as a vector. When plot is given a vector and no other arguments, it creates a scatter plot, where the x-axis is the index, or a sample, from the input data vector, and the y-axis comes from the values stored in the vector, in this case the duration of the eruptions. If we had used single square brackets, then the argument passed to plot would be a data frame and not a vector. So when the plot function receives a data frame, it will use the columns as axes. And since we're only specifying the eruptions column, we get a 1D scatter plot of the values in that column. Now, of course, we could specify both columns, or simply omit the square brackets altogether, since our data frame itself only has 2 columns, and then generate a plot of the eruption duration versus the wait time. Now, one thing to notice is that the plot function will attempt to do a few things for us. The creation of axis labels, for instance. If the input data is labeled, then the plot function will attempt to use those labels in the plot. We can, of course, modify or set these manually using additional arguments to the plot function, like main for the main title, xlab and ylab for the x and y axis labels. And for details on those, check out the help page for the plot function. There are also additional functions that we can use to specify things like the titles and labels. For example, if I write title and then pass a string, you'll see that it updates the main title for our plot. Again, for more information on these, do check out the help page for the plot function. For the next 2 sections here on stem and leaf plots and histograms, we're going to borrow an example from section 8.2 of an introduction to R, which is entitled Examining the Distribution of a Set of Data. So in this video, I'm not going to repeat their work, and instead, I'm just going to briefly introduce some of the functions and arguments they're using in the hopes that this will get you up and running with your own data more quickly. However, I do still recommend that you check out this section of the manual, especially if you're new to this type of analysis. So the first function I want to look at is the stem function, which generates a text-based stem and leaf plot. Using this function is similar to the plot function, except the stem function expects its input to be a single numeric vector. And so I must use the double square bracket notation to pass our column of data here. Now, the stem and leaf plot itself classifies or groups data according to the first or most significant digits. This is going to make up the stem on the left side, and then the leaf or leaves on the right-hand side are usually the next or last digit from each sample. And with only these two pieces of information, the stem function gives us the ability to view and get an idea of the distribution of the input vector. And so in this case, we can easily see that this particular data set is bimodal. In a lot of ways, the stem and leaf plot is similar to a histogram, and R also provides a function for computing or generating a graphical histogram. By default, given only a vector of data, the Hist function will generate a plot of the frequencies or counts of the samples that fall within each bin in the histogram. The histogram function does have lots of options for us as well. For instance, we can switch this histogram to be a probability density using the probability or frequency arguments. So for example, we can add prob equals true to use the probability argument, and we see that the left axis changes to a density rather than a frequency, and also the area under the curve is now 1. We also have control over the bins being used in the histogram. So at the moment we're using the defaults, but we can control the breakpoints by passing a sequence to the breaks argument. So perhaps we start the sequence at the minimum value in the data, which is 1.6. We can stop the sequence at 5.2, which is actually just beyond the max value of 5.1 in the data. And then we're going to use bins of size 0.2. Now, these values are hard-coded here and in section 8.2 of an introduction to R, but you can use the min and max functions to help you choose these values automatically for your particular data set. So there are actually several other arguments that you can tinker with to kind of get exactly what you want, but in addition to simply modifying this histogram, we can also add additional content to our figure by calling additional functions within the same code block here. For instance, we can use the density function with a Gaussian kernel to estimate the density from our data. Now, this is effectively a continuous version of our histogram here, but we can plot this on top of the histogram. So if I use the density function, pass the same column of data, faithful with eruptions, and then specify that I want my kernel to be Gaussian, and running this block, at this point, we actually get the output of the density object in text, followed by our figure containing the histogram. And what we really like is to draw this density on top of the histogram. So if we look here, the density object itself consists of two columns of XY data. And we can use the lines function to create a piecewise linear representation that can be plotted on top of our histogram. So to do that, all we need to do is pass our density object to the lines function as an argument. And now we see that we get a very smooth curve plotted on top of our histogram. But this is really smooth, and so the density function actually allows us to control this using the bandwidth argument. If we give it a value of 0.1, this gives us something that's perhaps a bit more representative of the data. So if in addition to this, we wanted to see the actual samples in our data, and not just the bins that we've created with the histogram itself, we can add a 1D plot of the sample data using the rug function, which will draw the sample x positions just above the x-axis. And we could certainly continue on like this for some time, adding more bells and whistles to our plots, but it's usually better for someone, especially who is new to this, to try out a few examples like these and then start to tinker and add things as they need or want. So I'm going to once again point you to the link to section 8.2, as it does continue on with this particular data and describes a few more functions specifically meant to help you understand the distribution.